And now we're ready for part C of question 2, our last application of vectors type problem, which still involves this same plane pi that we've used in parts A and B, but now also asks us to find the distance from the plane pi to a point P with coordinates 3, 2, 1. And once we've done that, then we're also going to find the point Q in the plane pi, which is closest to this point P. So how do we find the distance from a point to a plane? Well, pretty much any application type problem involving a plane will inevitably involve the normal to that plane, because it's the normal which really characterizes a plane. And what we'd really like here is the specific normal, which happens to start at the point Q, the one that lies in the plane but is closest to this point P, and joins up with a point P in either direction. It doesn't really matter which. Because that particular normal would be the straight line from the plane to the point, and so therefore the norm of that normal would be the distance from the point to the plane. But while we do have a normal to the plane pi, we found it back in part A, it's got components -3, -3, and 3, it's almost certainly not the appropriate size to represent this distance between the point P and the plane. So how do we come up with that normal? And the answer is we need to construct a projection. We need to find a vector which connects the point P to any point in the plane. It would be lovely if that turned out to be the point Q, but it almost certainly won't be, and that's okay. So we need a vector which connects the point P to any point in the plane, and then we can project that vector onto the normal that we've got. And the result of that will be a normal which joins the point P to the point Q. That'll let us find the distance, because then we just need to get the norm of that projection, and it will let us calculate the exact coordinates of this point Q. So that's the way we're going to approach this. So what do we need? Well, first of all then, we need a vector which joins the point P to any point in the plane. And since we've been given 3 points, A, B, and C, all along, we might as well use one of those points. And since C is kind of the simplest one, that's why I used it to get the equation of the plane back in part A, we'll use it again here, but I could just as well use the point A or the point B, and it really doesn't matter. Everything will come out the same in the end. So let's see, I'm going to join the point P to the point C. So I'll get a vector PC. And so in order to compute that, I need to subtract the coordinates of C from the coordinates of P from the coordinates of C, and those create my respective components of the vector PC. So in other words, my first component will be the x component, or the x coordinate of C, minus the x coordinate of P. That's -1, -3. The second component will be the difference between the two y coordinates. So in C that's 0, in P that's 2. So 0 minus 2. And finally the third component will be 1 minus 1. And so that gives me the vector -4, -2, and 0. Okay, so that's some vector which joins the point P to the plane, but it almost certainly isn't our normal vector. We could even check if we really wanted to and see if that's orthogonal to the vectors in the plane, but we can also figure that out just by taking the projection. And if it did happen to turn out to be, by some miracle, to be the normal we were after, when we carried out the projection, we just get the same vector back. That's all. Okay, so we're going to take this vector PC then, we're going to project it onto the normal that we computed back in part A. So let's call that projection P. So this is a projection onto the normal of this vector PC. And just in case you haven't watched the video for part A, I will put down again here that the normal we found there had components -3, -3, and 3. So computing a projection is just a formula we have to remember. Bear in mind that it's going to be parallel to whatever vector we're projecting onto, in this case the normal vector. So we just need a constant, an appropriate constant, multiplying the normal vector. And the formula for that constant is that first of all we take the dot product of the two vectors, so p, c, and n, and we divide that by the dot product of n with itself. And then we multiply, as I said, that by the vector that's being projected onto, which again is n. So pc dot n is going to be -4 times -3 plus -2 times -3 plus 0 times 3 divided by n dot n, which would be -3 squared plus -3 squared plus 3 squared. And then that's going to get multiplied by the vector -3, -3, 3. So a bit of computation to be done here. So let's see, in the numerator there we'll have 12 plus 6 is 18 plus 0 divided by 9 plus 9 plus 9 is 27 times the vector -3, -3, 3. 18 over 27 is 2/3. And in this case, we might as well multiply that into the vector because there is some nice simplification to be had here. And so that gives us the vector -2, -2, and 2. So that is another normal to the plane, but it's the specific normal whose size, whose norm, represents the distance between the point P and the plane. So finally then, we need that norm. And so the norm of this vector P is going to be the square root of -2 squared plus -2 squared plus 2 squared, which is the square root of 4 plus 4 plus 4 is the square root of 12. And we should simplify that. That's 2 root 3. And so there we go. That's the distance between the point P and the plane. Now, what's the point Q in the plane which is closest to P? Well, let's see. This vector P, this projection vector that we calculated, the vector that we projected onto it started at P and ended at C. Then this projection vector starts at P and ends at Q. So we can observe that the vector P is in fact the vector PQ, and we can use that fact to compute the coordinates of Q. It's really just doing what we did earlier to compute PC, but kind of backwards. So let's see, that means the vector PQ, if let's say Q has coordinates x, y, and z, then the vector PQ would be, again, the difference of the corresponding coordinates. It would be x minus 3, y minus 2, z minus 1. But that has to be the same thing as the vector P that we just calculated, with components -2, -2, and 2. So first of all then, x minus 3 has to equal -2, which means x has to be 1. Y minus 2 also has to equal -2, so y has to be 0. And z minus 1 has to equal +2, so z has to equal 3. So this point Q, that's the one that's in the plane and closest to the point P, it's the point with coordinates 1, 0, and 3. That finishes question 2. We'll move into matrices in question 3.